Hello, everyone, and welcome to this AGC Chemicals Americas webinar. My name is Katie, and I will be your Globalspec moderator. Now I would like to introduce today's presenter. With us today, we have Sarah Blosch. Sarah is a product and development engineer with AGC Chemicals Americas. Sarah, welcome to today's event. And with that, I'd like to pass things over to you to get us started.
All right, great. Thank you, Katie, for the introduction. And thank you, everybody, for being here today. I'm very excited to share some information about AGC, as well as some information on some high voltage wire insulation solutions. So before we get into the details of the science and the technical part of the conversation, I'd like to introduce our company. So AGC is a global company headquartered in Tokyo, Japan. We specialize in a number of different applications and technical spaces, with the biggest three in chemicals, electronics, and glass. So the company is, like I said, it's a global organization with the bulk of the employees being housed in Asia. We have some European locations and a plant manufacturing center there as well, and then a smaller but very strong contingent here in the Americas. So if we focus a little closer to where I am, we can see I work for a company called AGC Chemicals Americas. We are located about 30 miles west of Philadelphia in Exton, Pennsylvania. That is where our main offices are, as well as our R&D and technical center. We specialize at AGCCA. We specialize in compounding, as well as some textile and paper coatings and other type of high performance materials. My group specifically focuses on melt processable fluoropolymer compounds. But we also reach further than only fluoropolymers. We focus on other specialty materials, things like PEEK or PPS, really those high temperature, high chemical resistance thermoplastic materials. We have a manufacturing center in Thorndale, Pennsylvania. It's about 20 minutes drive from our headquarters in Exton. That is where we manufacture our compounds for global sales. So the materials that we produce in Southeast Pennsylvania get shipped globally all over the world. We have a very close relationship with our manufacturing center, allowing us to customize processes and materials for all of our customers and really hone in very specific custom solutions. So as we get into the main topic of the conversation here, I want to really focus in on insulation materials for consumer electric vehicles. So if we look a little bit broadly here at the power output for some already on the market electric vehicles, we can see here that if you look at the y-axis, that's peak power output. So as you increase on that axis, you have your higher performing vehicles, your probably much faster, faster acceleration. Potentially, you'll get some longer range vehicles in that area. But it's really important to note that we have EVs on the road right now that already exceed some of the requirements for the EV motor application space, specifically as we start looking into high voltage wire present in the EV motor. So this is a graph taken from an ID TechX report showing just some of your common or better known electric vehicles that are on the market right now, and showing the amount of power required or the peak power output of that vehicle. The reason why this is important and relevant for our conversation here is because the industry is moving toward higher power motors. As I kind of mentioned on the last slide, these higher power motors can lead to improved efficiency, longer vehicle range on one charge, faster charging to really get into that high speed charging that everybody so desires. This also allows for heavy duty vehicles, commercial vehicles, things that are going to really need a lot more power to run, right? That are going to be a lot heavier vehicles, things like that. It's also necessary for a higher power motor for electric aircraft. So if we look at eVTOL or your conventional takeoff airplanes, a higher power motor is required for that application. The things that we have in our electric cars today are not adequate for propelling these heavy duty either vehicles or aircraft. So what I want to do now is relate power output and how much power the car can produce to the voltage, because voltage is kind of what I'm going to speak about from here on out. Is we're going to talk about voltage requirements and how the high voltage wire insulation is affected by different voltage levels. So I have here the power law. It shows that power is equal to current times voltage. So as the power output increases, as the requirement for power continues to rise, either your current or your voltage must increase, or some combination of the two. In reality, it's probably going to be a combination of the two, but it's really important to note that the more you increase the current going through the vehicle, the more heat that will be produced. A problem that is already present in these electric motors is the cooling issue, is keeping these motors and keeping the vehicle cool as you're putting more and more current and electricity through the motor. So to try to avoid continuously adding more and more current through the vehicle, it means you need to increase the voltage, because one of those has to increase to create this higher power. So as I note here at the bottom, to accommodate higher power requirements, voltages must increase. So another kind of just background slide to just kind of really explain kind of some of the wording that I'll be using throughout this. I am going to switch from saying high voltage wire insulation and probably refer to it mostly just as magnet wire. So what I'm talking about when I say magnet wire specifically, again, as we look at consumer automotive electric vehicles, is I'm referring to the coiled magnet wire that is inside the motor stator, which creates an alternating magnetic field. That magnetic field, obviously, that's as electricity is passing through the wire, that's what creates the magnetic field. But as you get this alternating magnetic field, the magnets in the rotor will react with that field, causing the rotor to spin. And that spinning is what causes the wheels of the vehicle to move. So this is just kind of, I'm still kind of just trying to introduce the topic before we really dig into the insulation materials. So the last kind of to wrap up what I've talked about so far is that really wire insulation is critical for balancing EV power, weight, and thermal performance, because as you increase voltage through the vehicle, there's kind of, this is a roadblock, this is a stumbling block, something you have to, the materials that are present in the wire insulation currently cannot achieve some of these really high voltage, high power requirements. So understanding what insulation materials are available, what is going to be needed for the future for these EV motors is really, really key to properly designing and manufacturing either your wire or your motor or the automobile, at the very end. So what are our options? What materials are available, and what are the advantages and disadvantages of those materials? So I want to separate this into kind of two parts here. So over the next 20, 30 minutes, I'm going to talk to you about 6 different materials. 2 of those materials I can categorize as materials that are wires that are produced. The insulation is put onto the wire in an enameling process. So this process typically consists of dip coating your wire into a solution containing the polymer and some sort of solvent. The wire will then pass through an oven to anneal and solidify. And this can often take multiple passes as you go through. You have to continuously coat this wire to make sure there's no pinhole defects or voids of any kind, to make sure that the wire is fully coated and there's no voids, because at those voids, at those weak spots is where you will get your degradation, your discharge, and your failures. So polyimide are 2 of the most commonly used enameling materials. They have been used for years and years and years in this type of application, maybe not necessarily for EV vehicles, but anytime you see copper magnet wire in action, it's most likely coated in one of these materials. So more recently, some extrusion processable materials have kind of entered this application space. So 3 of those that I'd like to highlight to start are PPS, PEEK, and PFA. So those materials are all high temperature, specialty chemical type materials that can really withstand temperature, voltage. They're very chemically resistant, and they really, property-wise, really fit into this space very well. So an initial advantage of these materials is the fact that they are extrusion processable. Typically, extrusion is a bit more straightforward than the enameling process. You typically do not have to do multiple passes over the wire to get a really good, consistent coating onto the wire. And you don't have to worry about any of the solvents that might be necessary for the enamel process. So I'm sure if you're on this call, you're probably aware that PEEK is really one of the materials that is really being highlighted for this application right now as kind of the next generation material for 800 volt and higher motors. But I really want to discuss these other extrudable materials. And I also want to add one more to the list. So I also want to include ETFE in this conversation. So one thing I didn't mention when I was introducing AGC, so globally, we have a plant in the UK, as well as our manufacturing center in Japan, that produce both PFA and ETFE. They produce PTFE as well, but that's not as relevant to our conversation today. So they produce PFA and ETFE. So AGC Chemicals America is vertically integrated by having the production of these materials made by our parent company. So we feel very confidently that PFA and ETFE are very promising materials for this application space. Specifically, we are one of the worldwide leaders, if not the leader, of ETFE production on the planet. So we are very knowledgeable in ETFE as well as PFA. And ETFE and PFA are both very easy to process materials. They're extrudable, they're easy to coat onto wires, while AGC is generally kind of new to this application space. We are very experienced putting ETFE and PFA onto any number of wire and cable application, from downhole drilling to aerospace wire, to materials and wires inside internal combustion engine vehicles. So we really want to highlight those materials along with these other more traditional materials as we go through this conversation. So as we talk through this, there are a number of standards, specifications, different types of requirements for this application space, for the high voltage wire insulation space. It's really, it doesn't seem like an efficient use of our time for me to step through each and every one of these. This is just a small select few that I've got on the screen here. So I really want to focus in on three material areas, material requirements. Those three are adhesion of the material to the copper or aluminum core, the electrical performance of the insulation material, and the temperature requirements and the temperature limits that these materials can reach. I think these are three really solid pieces of information that are incredibly relevant to this application and can really highlight some of the advantages and disadvantages of the materials that I will show you next. So if we first look into adhesion, adhesion is incredibly important for the insulation onto the wire, because as I kind of mentioned when I was talking about the enameling process, anytime you get any kind of pinhole defect or void or some sort of deformation on the surface that allows the metal conductor to see the air, basically, that's where you're going to get discharges, and that's where you're going to start to have problems. You're going to get breakdown of the material, which will then lead to poor performance and honestly safety problems as you start looking at the function of the motor and its job, right? So adhesion of the insulator to the wire is paramount. So especially as you consider these newer hairpin wound wires that are used for more modern electric motor stators, they have these really sharp bends and really sharp folds that are going to exacerbate any voids or cracks or wrinkling that might be happening if your material is not adhering to the wire core. So now that I've talked all about adhesion, let's look at these actual materials. So as you can see on this graph, your enamel materials, the PI and the PAI, are your better performers as it comes to adhesion, with your extrusion materials maybe lacking a little bit more in that area. As I mentioned at the top of this talk, my specialty is in polymer modification and compounding. So we believe that we can take a material, and we don't just believe it, we put it into practice, and we have a proven record of taking these resins and improving them or adjusting them, manipulating them in some way that allows you to achieve the properties that you need for whatever the application is. So that is something we have done for this application space, for these high voltage wires. So I show here how we have been able to improve the adhesion of the PEEK, ETFE, and PFA materials. We have risen them to the levels equivalent to some of the enamel processed materials. So these have been tested on both flat and round wire, and we have tested them at different thicknesses, and we feel very confident in the ability of these materials to adhere to specifically copper. That's what we've tested more commonly. That's what most customers are most interested in. But we do have data showing that we can improve the adhesion to aluminum as well. So let's look at the maximum service temperature as well. I talked a lot at the top about how increasing current is going to increase the heat. So understanding how your material can survive in higher temperature atmospheres is very important for this application. So again, I note here higher power means more current, means more heat, right? So yes, we want to increase the voltage, but as I mentioned, it's going to be a balance of increasing both current and voltage. So what I show here in this graph is that majority of these materials have a maximum service temperature above 200 degrees Celsius. Usually that is the minimum needed for these electric motors. You can see the one material that I've really highlighted here so far is ETFE, and it doesn't perform quite as well as the rest of the materials. But as I mentioned with adhesion, through some polymer modification, we are able to increase that maximum service temperature of the ETFE to be equivalent to your PPS and close to some of your polyamides. It hits right around that 200 degrees Celsius mark, where we can show equivalent performance as it relates to maximum service temperature, which really shows that we can now promote this product, these materials, into this application space where the temperature requirement is a little bit more strict than some other areas. And so for the last one, looking at the electrical performance, obviously how the material performs in an electric, an environment that's taking on a lot of electricity is very important for an electric vehicle. So what I show here is the dielectric constant of these materials. So lower dielectric constant generally implies that it's a better insulator. It's going to need more electricity to break down the material than a material that has a higher dielectric constant. I'll talk on the next slide about PDIV, or partial discharge inception voltage. And dielectric constant, while not a linear relationship, is typically inversely related to PDIV. So lower dielectric constant means you have a higher PDIV, which is very important, as I will talk a little bit more about on the next slide. So as we show here in the graph, you can see that PFA is our best performer as it comes to dielectric constant. It has a dielectric constant around 2.1, where your enamel materials, your polyamide, your polyamide are upwards of 3 and above 3.5 in some cases. Your PPS and peak are still around the 3 to 3.5 range, and our ETFE usually hits somewhere around 2.5 to 2.6. So the fluoropolymers are better performers due to the fact that they have these fluorine atoms on the backbone of the polymer. That's just the nature of the material. The ETFE is not going to be quite as good as the PFA due to the fact that there are many carbon-hydrogen bonds on the backbone in addition to those carbon-fluorine bonds. So while but again, the fluoropolymer materials do tend to perform much better in electrical applications. And we see that again in applications outside of this one, but in our many years of experience putting ETFE and PFA into other electrical applications. So again, I want to highlight our ability to improve materials and improve their properties for a specific application. And I show here that we have been able to decrease the dielectric constant through, again, polymer modification or compounding. We can improve the dielectric constant by making it lower for the PPS and the peak. So we have lowered these almost to, and in some cases, even past the level of ETFE. So to kind of summarize everything I've talked about on this slide, I really want to show not only what the different material options are, how they behave in these 3 different categories, but also really highlight the ability of AGC, specifically AGC Chemicals America, to improve materials to further advance them beyond what the base resin, the base material can do on its own. So let's talk about partial discharge inception voltage, or PDIV. So on the right side of this slide, I kind of just have some points explaining what that is for anybody in attendance who might not be as familiar. So this is a measure of the minimum voltage needed to cause a partial material breakdown. So really it's about overcoming a threshold. So usually when you're performing these tests, you will set a specific threshold and say, once there's enough electrical activity past this point, that's the partial discharge inception voltage. So at what voltage is that threshold passed? So PDIV is, so partial discharges are small electrical discharges that happen within the insulating material. This is most commonly at voids or weak spots. Again, as I mentioned, having any kind of pinhole defect or delamination or cracking present, that is going to really affect your PDIV. Those specific partial discharges are not full breakdowns of the materials. So this is not the same as a breakdown voltage or dielectric breakdown test. Partial discharge, as it says, is just a small electrical discharge, a small or a partial discharge happening within the material. However, continuous partial discharges over time will start to lead to material breakdown and degradation. So one thing I should note is, yes, partial discharges are more common at voids or weak spots, but they will always start to happen in any material, no matter the coating. So even if you have the most pristine, best coated material ever to exist, you will still get to a certain voltage where partial discharge will start to happen. So as I mentioned here, better insulators, materials with higher dielectric strength or lower dielectric constant, can withstand higher electric fields before breakdown occurs. So that's partial discharge in a nutshell. The next thing I want to talk about before we actually start to look at the data on this graph is that PDIV measurements are very specific to how they're measured, the form of the sample that you are testing, the atmospheric environment that they are tested in, as well as the instrument itself. One PDIV tester is not going to be the same as your neighbor's PDIV tester. They can analyze and detect the data in different ways. Some are more consistent and accurate than others. If the insulation thickness is incredibly important for this. As you get much thicker insulation, that's going to give you higher and higher voltage data, higher PDIVs. And the reason I say this is because it's really easy to look at a material specification or a technical data sheet and say, this company can get a PDIV of this number, this company doesn't get that high. It's really important to understand how those materials are tested and really make sure you're comparing them as as you would say, an apples to apples comparison. So with all of that said, let's look at this data that I've got over here on the left of the slide. So these materials were all measured on the same instrument within the same probably half hour of time. These were coated flat wire, rectangular wire samples. The insulation thickness was around 150 microns, and our threshold that we had to elevate above before we, to determine what the PDIV was, our threshold was 100 picocoulombs. So not surprisingly, the PFA and the ETFE, the materials that have the lowest dielectric constant, were our best performers in this situation. And if I were to go back to the previous slide, which I will not, but if I were, you would see that we follow the exact opposite trend. As I mentioned, they're inversely proportional, typically. Again, not in a linear fashion, but the inverse of the behavior of your dielectric constant will give you your partial discharge inception voltage behavior. I will also note that I don't have PI on this graph, and that's because I did not have a sample of polyimide coated wire at the time. And like I said, it's unless you're comparing materials in a equivalent environment, your data is not going to mean as much. So I also want to talk about the impact of temperature on PDIV. So I show here on the right the PDIV change over as the temperature increases. So starting at room temperature and then increasing all the way up to 200 degrees Celsius. These materials were thin films of approximately 100 microns thickness. Our PDIV threshold was the same, but one thing I want to note, as I mentioned about the way this test is performed, these tests were performed on a different instrument. So you'll notice that our maximum PDIV for our PFA material on the graph on the left is almost 1,600 volts, whereas on the right, it's only around 1,100 volts. Another thing to consider there is the type of sample we were testing, a film versus the wire, as well as the insulation thickness. Typically, as you decrease the thickness, your PDIV will go down. So just another, I think, a good example of why understanding how the materials were measured is very important for this test. So if we look at this data, there's a few things I want to point out. I was only able to test peak, ETFE, and PFA as well as two compounds, one based off of ETFE and one based off of PFA. And what we can see here is that generally all of the materials, the PDIV goes down with temperature, and that's expected. Again, the PFA is our best performing material. It does have the highest PDIV compared to these other materials. But one thing I really want to highlight here is the behavior of the ETFE materials. One kind of innate property of ETFE is that with temperature, generally, the electrical performance remains relatively the same. You can see we don't see nearly as much of a decrease in the ETFE performance for both the resin and the compound as we see for the peak and the PFA. You can see here that the peak material outperforms the ETFE at room temperature, but as you get past even around, we'll say 60, 70 degrees Celsius, the ETFE is a better performer because it really stays relatively constant. So it's just the nature of the material. Again, the PFA is still your best performer, but ETFE absolutely performs well enough in high temperature environments. So as I kind of start to wrap up and summarize here, I've got a couple more slides. Just to reiterate what I've said previously, that as we look into the future globally, as the global EV market continues to increase, the power output of those vehicles or airplanes or whichever application we're speaking about is going to continue to increase. So again, what this does is improves efficiency of the vehicle, allows for longer range, faster, higher performing vehicles. It also allows for faster charging. And as I already said, it allows for heavy duty vehicles, commercial vehicles, and then aerospace applications, whether that's vertical takeoff vehicles or conventional takeoff vehicles. And then I also hope that I was able to highlight not only, the entire landscape. I did not cover every single material here, but a glimpse of the landscape of the insulation options. I hope that I was also able to show that AGC has the ability to customize materials for any application, and that we have currently commercial materials and commercial resins that can meet many of the current market needs here. We also have solutions that can already meet many of the future needs, and development is underway to really meet and exceed the EV motor of the future. So what we're doing in terms of development, and how I'll wrap up here, is we're doing studies on continuing to improve our PDIV measurements, not just the measurement, but the way our materials react to the test. So we're trying to increase the PDIV values for our materials. We're also doing a lot of work looking into developing low outgassing materials, so materials that don't have harmful gases produced as they're extruded. We always are keeping our keeping our eye on and making sure we're within any kind of regulatory guidelines, and we're always looking toward creating more sustainable solutions. And we want to continue to work with our development partners. We've had some great partnerships with Rosendahl Nextrom, who created flat wire, rectangular wire samples for us. Newt, New England Wire Technologies, who has worked very closely with us to make round wire samples, as well as Marpos, who has helped us to test these materials, do some of these PDIV and electrical testing, to get us the data basically that I showed today. We look forward to continued work with these partners, as well as hopefully developing new development relationships with other suppliers, other manufacturers, other vendors of these types of testing equipment and such and so on. So with all of that, I would love to thank you for your time today. Thank you for your attention. Please feel free to ask questions in the chat, and I'd be happy to answer as many as I can. And also feel free to reach out to either myself or our senior sales manager for the automotive market. His name is Joe Stoikov. I have his information here as well. And we look forward to hopefully answering your questions or working with you soon.
All right, Sarah, thank you so much for that great presentation. All right, Sarah, so let me move to our first question here. What are the most common failure modes for insulation in high voltage EV motors?
Thank you, Katie. So some of the most common failure modes are some of the things I've touched on. Again, any type of void or crack or delamination between the metal core and the insulation. That's the most common place for failures. So that's why adhesion is really important for this application, especially, like I said, as you look into the hairpin wound materials, the materials that have these really sharp bends. That's where it's really important that you have material that is well adhered, uniform insulation coatings, and so on. So those would be what I would consider more of some of the common failure modes.
Right. Thank you so much for that answer, Sarah. So in the queue here, this person's asking, it seems PDIV changes a lot every time you test. Is there any industrial standard conditions?
That's a great question. So there are IEC and ASTM standards for testing these materials. The problem is, like I mentioned, there's no standard for the equipment used for testing that information. So, some instruments will use an antenna, some will use a coupling capacitor to interpret the data, and that will lead to very large fluctuations. It's something we have looked into quite heavily as we've been working on these materials. So while there are standards in terms of how to prepare your sample and potentially what the voltage increase should be. So again, this test is performed by just increasing the voltage until you hit that threshold. There are some standards and specifications for that, but beyond that, there aren't as many specific ways or requirements for testing that value.
Great, Sarah. Next one here. Are there inorganic fillers that you believe are useful to improve PDIV and or maximum service temperature performance?
We have done a decent amount of testing on some different inorganic fillers, specifically for improving PDIV. The only area where we're seeing any kind of promise there would be more in terms of the process. So if you can potentially add in, if you can add in like a foaming agent, so you're controlling pore size, or if you potentially like a glass filler that's hollow of some sort, those types of things could potentially improve PDIV. In terms of things like just other inorganic fillers, that typically doesn't support that. And then as it comes to maximum service temperature, typically we have seen that it either doesn't have much of an effect, or in fact it might make it worse depending on the filler. So that's what I would say. So there are some that can help with some of the electrical properties, but in terms of the temperature performance, nothing that we have studied at this point can help with your maximum service temperature.
All right. Thank you, Sarah. And next one here in the queue. Can a single material meet both electrical and chemical resistant needs? Are there multi-layer systems better?
Sure. So a lot of, there are examples of multi-layer systems that, for example, there's some that have maybe a polyimide interior and maybe a PEEK or some other material, or another, maybe like a polyimide on the exterior. And the purpose of that is generally to improve the voltage, the electrical performance, as well as create more chemical resistance. There are materials that can adequately, adequately meet the needs in both of those areas. I would highlight the ETFE and PFA materials that are more capable when it comes to electrical performance, but are also innately very chemically resistant. So and in general, a single layer solution is ideal, right, in terms of processing both time and difficulty. But, there are materials, like I said, the PFA and the ETFE, that can meet both of those requirements.
All right. Thank you so much for that answer. We've got a couple more questions in the queue here, Sarah, so I'm just going to grab this next one.
Sure.
Can insulation materials be customized for specific OEM requirements or design constraints?
Absolutely, and that's what I hopefully showed in some of the data here is that again, one area where I think AGC really excels is in our ability to create custom materials and custom solutions for whether that's the OEM tier 1 or tier 2 level supplier or manufacturer. Working at all of those levels, I think we can help design custom materials for any application.
All right, great. Thank you so much. Next one. Do you add any fire retardants when compounding your resins? Will it help?
So that's a great question. ETFE and PFA fluoropolymers are generally all V0 already. A flame retardant isn't required. The only time we would add a flame retardant is if the application was outside of the general scope of what we're talking about here. So maybe it's a super oxygen-rich environment, or if you've added some other filler that might be affecting the flame retardancy. But for this application where we're just in normal atmospheric conditions with some heat, flame retardants aren't needed, especially when we consider the fluoropolymer materials, the ETFE and the PFA.
All right, thank you so much, Sarah.
Sure.
All right, moving on to our next one here. We've got a couple more left. All right, how does insulation choice affect overall motor efficiency or weight?
Sure. So insulation, depending on the insulation you choose and the voltage you're trying to achieve, can absolutely affect the overall efficiency and weight of the motor. So if you have a material that performs better electrically, it can allow you to have a thinner coating. So a thinner insulation means that you can fit more wire into the motor, or it's going to make your motor weigh less, right? So less insulation, less weight, or more copper, more performance, right? So if you can choose a material that allows you to insulate at a much thinner thickness, that is really ideal for improving efficiency and weight of the motor.
What's cheaper insulation system for EV motors?
The cheaper insulation system, that's a good question. Because what it really comes down to is, again, the thickness of the coating. Obviously, the thicker coating will required, the more material you would need, and will likely cost you more. So also, these materials are sold at very different price points. So, the less expensive material and the thinner the coating you get, the better. We have actually recently done some pretty thorough calculations to determine basically the dollar per volt. And while a lot of people tend to be concerned that PFA is a denser material, so the question being, well, do you need, are we going to have to buy more because the material's denser? The answer is no, based on the price of the material compared to some of the others, as well as the performance of that material compared to others. It still ends up being the least expensive option of some of the materials I've listed here. I should say, let me give a quick caveat to that. That's of the extrusion processable materials. I can't compare, mostly because I'm not as aware of the processing cost differences between enameling an enamel process and extrusion process. But when it comes to extrusion processable materials, we still see in terms of performance value that PFA and ETFE are very, very favorable in that respect.
All right, Sarah, thank you so much. So we've got time for one more question today. So I'm just going to grab this one here, and then we're going to start to wrap up. So, all right, Sarah, last one for today. How do you evaluate long-term reliability when introducing a new installation material into an EV platform?
That's a really good question. So um, there's a number of tests that are out there for determining long-term performance, long-term performance, not only based on voltage, but also on thermal performance. So there are different standards out there for testing that. What we have seen, and if you want those specific standard names, you'll have to ask me after this because I don't have the numbers memorized. I'm sorry. But what we have seen when we're doing some of our partial discharge inception voltage testing is that our materials, while not only performing at a higher level when it comes to the voltage, it also, what we've noticed is that less discharges are happening once you get to that voltage. So if you've ever seen this test performed, you can see in certain softwares, again, with our partners at Marpos who have been instrumental in getting this data, what we've seen is that specifically for ETFE and PFA, once we get past that threshold, we're still getting a much lower quantity of these partial discharges. So basically what that means, as I mentioned previously, is that continuous partial discharges, continuous breakdown of the material or continuing constantly discharging is what will lead to the breakdown. Sorry, that wasn't very graceful. But more and more partial discharges are going to lead to material breakdown. So even with our materials being able to achieve a higher voltage, there are also not as many discharge events are happening even at those higher voltages, meaning that the longevity is increasing. So we'll actually be presenting, I believe, one of our European colleagues will be presenting on some data about that specifically in the coming months. So anyway, there's some standards, there's some anecdotal, but future actual studies on this to determine that long-term reliability.
All right, Sarah, thank you so much for answering all of our attendees' questions and for such an amazing presentation. We are going to start to wrap things up right now, but I just want to say a huge thank you to you for being here with us today.
Thank you very much. I appreciate everyone's time and thank you for your help, Katie.
Again, everyone, thank you all so much for taking time to attend this webinar event. Take care, and we will speak with all of you soon.